Hopefully you enjoyed the dynamic routing protocol. So now we're getting more specific. This is the main routing protocol that we have in the CCNT, and it's OSPF. EIGRP doesn't come in until CCNA3, and so we have OSPF and only single area OSPF, even though they throw in little things about multi-area, which again is something that comes in CCNA3. So what we're going to do here, we're going to explain the process by which link state routers learn about their networks, describe the types of packets used by Cisco IOS routers to establish and maintain an OSPF network, explain how Cisco IOS routers achieve convergence in an OSPF network, configure an OSP router ID, configure single area OSPF version 2 and a small routed IP version 4 network, explain how OSPF uses cost to determine best path, verify a single area OSPF version 2 and a small routed network, compare the characteristics and operations of OSPF version 2 to OSPF version 3, configure single area OSPF version 3 and a small routed network, verify a single area OSPF version 3 and a small routed network. So basically we're doing both OSPF version 2, which is IP version 4, and OSPF version 3, which is IP version 6. So evolution of OSPF happened over time, right? That's our current ones that we're using are OSPF version 2 and OSPF version 3. Features of OSPF. It's classless, right? So remember we had classful with RIP version 1. OSPF is always classless. Some of these can be classful or classless. OSPF is always classless. We always put in the subnet mask with it's always transported in the routing update of OSPF. It's efficient. Routing changes trigger routing updates. Alright, no periodic updates. If there's a change, it makes it. It uses SPF algorithm to choose the best path. It has fast convergence, like I said, 1 to 3 seconds. Scalable. It works well in small and large networks, so we can start off small and scale through areas. It has this thing called a DR running it and a BDR backing it up, and so it makes it hierarchical. It's secure. We can use MD5 authentication, which just means we can password it and have those passwords protected with MD5. Its administrative distance is 110, and that's all versions of OSPF. As you can see, EIGRP summary is 5, EIGRP external is 170, and EIGRP itself is 90. And I apologize because I feel like in the last one I told you that EIGRP summarized was 20, but maybe not. Anyways, it's 5. Okay, so components of OSPF. Builds a database. Where does the database come from? The neighbor table. Okay? Or how do we see this database? The neighbor table. Alright? Builds a link state. And that's the adjacency, right? So this is where we're getting hellos. How do we see who we're getting hellos from? Bam. Show IP, OSPF, neighbor. And these will be important commands on your CCNA. These are symlets, which means you have to issue commands to answer the questions. So that's one of them. Show IP, OSPF, neighbor. Our next one, we have a link state database, which is the topology table. How do we see that? Show IP, OSPF, database, right? So this is all of the network information, or all of our router information and the networks they go to, basically. Then we have our forwarding database, which is our routing table. Show IP route, just like we had before. Show IP route. Okay, so those are our tables that make up our routing. We're going to find out more about what they're talking about there in a second. I don't really like that picture, so we're just going to keep going. So, what happens? Link state operation. So we know from the last chapter that the routers send hello. Okay. Then the routers exchange link state advertisements. From the link state advertisements, they create their topological database, and then they run the SPF algorithm on that. They create the SPF tree, which is the map, and yeah, so there's your map. Alright. Single area versus multiple area. So in single area, we just have area 0, the backbone area. We actually could do any area if we're just doing a single area, but since we want to be able to scale, we want to build networks to scale and not be flat, and so we keep it in area 0. Now a multi-area is where the backbone, all areas have to connect to the backbone, so we have 51 over here and 1 over here. For them all to talk, they have to connect to that backbone area. Here's the best part about OSPF. You're not going to like it, but OSPF uses the IP address of 224.0.0.5 and .6. One is to the routers, or one's to the DR, and one is to everyone else. They're multicast. We'll talk about those in a second, but anyways, breaking those down into layer 2, so it tells us our layer 2 is going to be 01005E, which is, we know that's whenever we see the 224, the multicast at the layer 2 is 01005E, and then we take the other numbers and put them as the rest of our address, which is 00005 and 00006, right? Or just 6 and 5. Our layer 2s are right here. Then OSPF uses, so this is our layer 2, our layer 3, our layer 4 protocol that OSPF uses is actually called OSPF. EIGRP uses RTP, which is Reliable Transport Protocol, not real time, from VoIP. If you guys are familiar with that. And then in our packet specific information, like I guess this is our application data. It has, I don't know, it contains the OSPF packet information, right? So let's see if we can see some. So our packet types would be hello, database, link state, link update, link acknowledgement, which we're going to talk about next, I believe. So 1, our hellos, used to establish and maintain adjacencies with other OSPF routers. 2, contain, now these are LS, these are the link state packets. So yeah, this is forming adjacencies and passing routing information. So first, to form our adjacency, we use these hellos. Alright, so the be type 1 being sent back here, this would be a type 1. Then we have database description packets, which contain an abbreviated list of the sending router's link state database, and is used by receiving routers to check against the local link state database. The link state database must be identical on all link state routers within an area to construct an accurate SPF tree, right? So remember, they keep the same map, and so this is the thing, checking to make sure they all have the same map. So then we have a link state request. Receiving routers can request more information about any entry in the database description packet by sending a link state request. Type 4, a link state update, is used to reply to the link state request. So if someone wanted more information, they would then receive an LSU, and then a link state acknowledgement acknowledges that they received the link state update. So what's in the, now we have this information, probably isn't as important, but it tells us, remember, we have the different types inside that packet information. It says type 1, and then we have the router ID and the area. And so we're going to talk about router ID in a second, but the router ID is just a thing that identifies, it's going to be how we elect our designated router, if there's a designated router, depending on the type of network we're in, depends if we elect a designated router or not, but we do that through the router ID. The area ID is, well, that's what OSPF area we're in, so for single area, hopefully it's area 0. Then we have all of our other information, and in OSPF, our hello interval and our dead interval have to match to form an adjacency. That's why they're sitting here. In EIGRP, they don't, but in OSPF, they do. All right. Designated router is the boss, if there is one, right, of a multi-access network, and then the backup is what's going to send the changes to those who need it if the designated router goes down. Then list the neighbors, because we have to build this whole map, right? Okay. So hello packet intervals by default 10 seconds on slower networks, non-broadcast multiple access, which is like frame relay, which we'll talk about CCNA4, don't really exist that much anymore that I know of. They go 30 seconds, but on our Ethernet networks, they're going to go 10 seconds. And for whatever reason, they're now telling us about our IP version 6, right? So here, this is a good time to talk about this. 224, that's our IP version 4. So broadcast for link local addresses, which that's what our IP version 6 routers use, link local addresses as the source for updates, and then they use FF02::5 and FF02:6 for the others. And so it's saying that FF224005 are transmitted. That's the destination that these routers will use. So what that allows is it can go to multiple. The hellos can go one to many, right? So if this was a switch, it could go to multiple routers, whereas I guess they'd have to just send them out on each link how we currently see them. Then our dead timer is 4 times the hello timer, so on a normal, if 4 times would be 40 seconds on our 10-second network and 120 seconds on our non-broadcast. Link state updates. A link state update contains one or more LSAs, and if you're asking yourself what is an LSA, we are about to talk about these LSAs, but basically it's just routing information. It's how it builds the routing table. So alright, so here's our election process, which will happen. And you will probably only see, typically, if you're watching it, it's so fast that you usually see initiation state and full. Maybe loading sometimes, and maybe two-way. If you're having problems, sometimes you see two-way. So to form the adjacency, first we don't have an adjacency. Then goes into the initiation state. Once the neighbor adjacency is formed, we're in the two-way state. From there, we start the exchange start state. So this is where they're synchronizing databases, and then they start exchanging into the exchange state. The loading state is loading what they've just exchanged, and when they've became a neighbor, they're in the full state, full loading. So that's how OSPF moves, and like I said, you probably will never, unless you're having problems, you don't even have to worry about this, but there will be multiple drag and drops that ask questions about it. So how do you establish neighbor adjacencies? Well, first it goes from down state to the initiation state. What does this actually mean? Hello, my router ID is blah. Is anyone on this link, right? And it says, yeah, I'm in the same network, so we can talk. So then it goes in two-way state and sends all the stuff, and it picks out the DR and BDR of this network. Sure, that's I think an easier way to understand it is the reason. So in OSPF, how the DR is chosen is the highest IP address. So we have this one of 5.2 and this one of 5.1. So as you can see, but they changed the default priority. What? I think they got this wrong because the DR should be the highest IP address, and it's saying that they are second highest router ID. This actually what? Oh, no, I just read how the traffic was going. So this is .2, and this is .1. So yeah, this would be the DR. I thought it was saying this was the DR though from the graphics. So anyways, how it selects the DR, right, is the highest IP address or the highest router ID, and we can set the router ID, or it can takes it first by the physical interface, then it takes it by the loopback, and then what we manually set. And so I think that's what we're going to study next. And so the DR and the BDR are like the king and queen of the realm of OSPF area, right? So they make all the decisions, or that's who everyone gets their orders from. So after these are all flooded, which now it's going to talk about adjacencies, which this is kind of just talking about the more routers we have, the more adjacencies we have. We can get that by n times n minus 1 divided by 2. Shows us how many adjacencies. The more adjacencies we have, the more flooding of LSAs makes it bad, and this is why we kind of want to go into a multiple area, right? Because when we flood these, there's too much flooding, then it takes too long in convergence and all of that. But basically the LSAs are sent to the DR, and then the DR tells everybody else what they need to know, is what we're seeing there, and how it's elected. So what do we have here? So who sends the first? DBD, remember, which is how they check their databases. Whoever has the IP address is going to become the DR, and so they also, since they're the boss, they get to send the information to everybody else as well. And so that's what we're seeing here. They check them. If they need more information, like this one need more information, send a link state reply. The DR sent back a link state update and then acknowledged getting that information, because if it didn't, then it would have to keep going over that. So now we go to our router ID. And so in our little areas, we're going to have a router ID. We go into router configuration too, and this will make more sense once we set up OSPF, but it's a lot like RIP. So we go into that IP, or we just say router OSPF, and then we put that number, which was talked about in the last chapter. But then inside of there we can put router ID and actually put a value, right? 1.1, 1.1.1.1 to 25.25.25.25 is our options. And the higher the number, the more likely it is to become the router ID. So if we always wanted something to be our designated router, we would give it a 255.255.255.255, right? Just 4 255s. But how it picks it without setting a router ID is, so if we set the router ID, that's how it gets it. If not, it says, hey, do we have a loopback? What's the highest loopback configured? Okay, we're going to pick the highest loopback, highest IP address on our loopback. If there's not one of those, then use the highest IP address, active physical IP address. Now, why do we use a loopback or a router ID over this physical address? Remember, a physical address, what if the other side turns off? It goes down, so our DR becomes unstable. So the loopback's a virtual interface, so it's more stable, but then me programming it in because I want it to be the router, want to give it a router ID, is the most important. And so they're going to show you the commands to do that, right? Router OSPF 10. Remember this number. This is just a identifier. It can't be 0, but it can be any number, but it means nothing. It doesn't have to be the same on any router. And then we go in and put a router ID. I think this is a strange thing to teach you first how to configure OSPF, right? If we want to modify it after we set a router ID, we actually have to type a clear IP OSPF process command to rerun the algorithm, to rerun Dijkstra to say, hey, this is my, this could be my DR, right? We have to say clear IP OSPF process from the privileged exec mode. We could use loopback. Not going to worry about that because you're never going to be tested on it. Alright, so how do we enable OSPF on networks? Well, one, we got to go over what's called the wildcard mask. And so a wildcard mask is the opposite of a subnet. So we take any subnet and we subtract it by 4 255s, okay? And that gives us our wildcard mask. So a 255.255.255.0 becomes a 0.0.0.255. And it basically shows us how far away our next network is, right? Like if we had a 192, want to know how many hosts away it was, we could just take it through this. Like say we had 192. Oops, this is going to be junky. Nope, we're not doing that. So we have 192, 168. 1.0, the subnet of 255.255.255.192. If we want to see where our network ended, we would just add this, right? So our network would end at 192.168.1.63. That's one thing a wildcard can do for us. Other than that, it's just what we use in routing protocols and in access control lists. But make sure you read over that because these wildcard masks are not going away. Alright, so then what we do is we say router OSPF 10, kind of like we did router RIP, right? Except we have this number now. Router OSPF 10. Remember, this doesn't matter. It's just a process ID number. And then we say network, then we say the network that we're doing. But then we do the wildcard mask for that network, and then make sure we tie it in to area 0, or whatever area it's going to be in. So that's how we program, and that's going to start broadcasting hellos out of our interface that's associated with. Once again, we can use a passive interface, and if you forgot from the last chapter, passive interfaces be used here, here, and here, because routing information only needs to be shared within routers. These are like switches and layer 2 areas. We only need layer 3 routes for layer 3 devices, and so these are the only guys that need to share the routing information. And so we use a passive interface command where we don't need it to secure it, and just so we aren't wasting bandwidth and that kind of thing. So how do we do that? Same as with RIP. We just go into router OSPF 10 and say passive interface and the interface that the device is connected to. If you guys want to try that, feel free. Okay. So then we get to, and that's all. I mean, it's virtually the same as RIP, except wildcard mask, and it just works, and it's easy. If we want to advertise it, we just put it in there, forms neighbor adjacencies, and starts working. It is a beautiful protocol. I would definitely try it out if you haven't. Anyways, but how we get cost, and this is, we sometimes adjust cost, because as you guys can see, 10 gig is calculated the same as 1 gig or 100 meg, right? So it starts being inefficient because when this was initially made, right, it was made for networks of where 10 meg was fast and 100 meg was really fast, right? So now that we have 10 gig and 40 gig, and I don't know what it would do if we had 100 gig, right? We have to actually adjust our cost. But basically, we take our speed and we divide it by 100,000, right? And that gives us our cost. Or we take 100,000 divided by our speed, sorry. And that gives us our cost. Unless we adjust it, right? But how OSPF calculates cost, right, is 64 plus 1, right? So this is 75, where this would be 64 and 64 plus 1, so it would be 129 going this direction, right? Because this would be a 64 link, this would be a 64 link, this is a 1, so that's 129, where this is a 64 and a 1, so it would be a 65. It's going to pick the lowest cost. That's what cost is, but like I said, we do have to adjust it sometimes. So what are they telling here? Hit the bandwidth command. Anyways, this is talking about adjusting using the bandwidth command. So from the past screen, it was just saying that these serial interfaces do not calculate bandwidth correctly, and so if we want to adjust that, we use the command bandwidth on the interface. So as you can see up here, bandwidth 64, so we'll calculate the bandwidth as 64, or calculate the cost correctly. The interface serial bandwidth 64. This does not set the speed, right? The speed command sets the speed of the interface. Bandwidth is purely for EIGRP or OSPF to calculate a metric based on cost, or they both use bandwidth. One uses bandwidth and delay, one just uses bandwidth. And so that's what the bandwidth command is for, is so that the metric is calculated right, not a speed. It does not change the speed of an interface. So then we can manually set the cost, right, like I said, so that it'll fit 10, and never mind. This is manually setting the cost, not manually adjusting how the cost is calculated. So we go into the interface and say IP OSPF cost, and actually put a cost on there, and so that cost would be how it would calculate that link, right? So it would add 1500 or 60, whatever you calculated, it would add that cost. Should have been. Here it is, adjusting bandwidth reference. I must have missed the command here. It must be here somewhere. Here it is. So we go into router OSPF and say auto cost reference bandwidth, and then set it into the megabits we want. So if we want to set it for gigabit, we'd say auto cost reference 1000, whereas if we want to send it for 10 gig, we'd say auto cost reference bandwidth 10,000, right? Okay, so that's how we adjust that part. These show commands, once again, these are going to be important. On your CCNA, they do a lot of these commands, so show IP, OSPF neighbors. this showed the adjacency table. Maybe you remember from the beginning of this chapter, right? So it shows anybody sending hellos. So if you're wondering why you're not forming an adjacency and you issue this command, show IP OSPF neighbor, and you don't see a neighbor in that table, then it doesn't exist. It also shows what state you're in. So if you're stuck in a two-way state, you know that you haven't formed a full adjacency. So it could be that there's a password on, there could be a lot of things going on. Maybe you change the hello timers or something like that. Okay. Show IP protocols. We saw this one with the RIP. It'll just show us. It'll show us all the routing protocols running. Shows us important information about them, right? What networks they're coming from, where we're getting our sources. These are router IDs down here. What the actual router ID is of our device, and just that kind of stuff. Show IP OSPF is going to show us, I don't know, stuff that really isn't very. It shows us some of the same stuff from protocols, but then it shows us like kind of LSAs we're supporting, right, and just stuff like that. This NSSA is not so stubby area, and it's just a type of area, so it's going to show us what type of areas. I don't know. It's showing us a lot of things, but not necessarily. I don't know that we need to see it. But these show commands, like I said, they might come in handy when you're doing your lab sim or in real life. Sometimes you have to use a lot of show commands. The thing about layer 3 problems is when they never happen until they do, and then when they do, that's when you have to really know how they work. So we have a show IP OSPF brief. So in if we have just point-to-point network, there's no DR election, right? So we see that this is point-to-point. On the serials, of course, they're point-to-point, right? And then this DR means it's a multi-axis, and so multi-axis would be either, there could be even a switch in between these, but anyways, there's multiple. It's probably a switch in between these. We could have them, something like that. So there's multiple paths, that kind of thing. Anyways, that's what we see there with the show IP OSPF interface brief. There is a lot of command questions on this one. Alright, so OSPF, the similarities, they're basically the same. They are almost identical. Where their differences are is on the advertisements, right? We're going to send to what we've already talked to, the FF02::5. That's to all routers, right? And then the FF02::6 is to the DR and BDR multicast, right? And where we had 2246 was the DR BDR, and 5 was just the routers. Instead of using the network command, we just put a interface into it, right? So we go into router ID, we go into IP version 6 router OSPF, let's say 2, and then instead of putting all of our stuff in there, we just set a router ID and move on, a 32-bit router ID. And we also have to issue, just like we did with IP version, with RIP, IP version 6 unicast routing, right? So we have to do that. But we're configuring this at the interface level mostly, and we don't have to actually put the actual network on, as it's programmed into the interface. The other difference is our source IP version 6 addresses are linked local addresses, and then they're sending to these multicast, these link local multicast addresses are their destination. And that's how the routers talk to each other, rather than the physical IP address and then a multicast. It's the link local address and a destination of this FF02 in either 5 or 6. Alright, so we have our network topology. Hopefully you guys remember some IP version 6 stuff, right? But if you don't, I guess you can copy this out, kind of try this in your own lab, see how it goes. Anyways, so keep going. We enter this IP version 6 unicast routing, and then they put the IP addresses on. So hopefully, if you forgot how to put on IP version 6 address, this is how you do it. Oh, they're not going to show you. Okay. Or is it lower? Okay, well, it's not there. But what you would do is you would configure the 32-bit router ID. And how you would do that, right, is the router ID command just like you did before, but you'd say IP version 6 router OSPF. That's what allows you to do OSPF version 3. IP version 6 rather than just router OSPF. And then the number. And then we'd go in the router ID and assign it. And this is an IP version 6 address. This is still same as what we were doing before. And then we could adjust the reference bandwidth if we wanted to. But then we go into each interface and we just say IP version 6 OSPF and the area command. And then it puts it in an area and it's going to work. For whatever reason, they want you to really focus on the link local addresses in here. It shows you how to change a link local address. We've already done this in some packet tracers, but just IP version 6 FE80 : something. And remember, we don't put a slash on it. We say space link local to set the link local. Let's see if there's anything important down here. Nope. Anyways, so that's optional. We do not have to do that. Back to router ID. Here's enabling it on interfaces. Maybe we'll have some show commands for us. So as you can see, you went into interface G0 and we put it into area, like I said, IP version 6 OSPF 10, then the area, and then did the same thing for the serial, right? And that's how we do it. It's kind of easier because we don't have to remember the network, we don't have to do anything, we just go in the interface, it either works or it doesn't. Our verify commands are the same as with IP, except we say IP version 6 OSPF neighbor, IP version 6, show IP version 6 OSPF interface, show IP version 6 route, OSPF, those kind of things. But they're the same exact commands as what we're using IP version 4. But make sure you go through those, because if you don't, like I said, there's a lot of show commands, or a lot of commands on this test, and there's a lot of commands on your CCNA certification. So I hope you enjoyed that. If you have any questions, please send me an email or post on the forums. Thank you.